For Part 1, Working with Amazon SQS Messages. Let's walk through the life cycle of an Amazon SQS message. First, a producer sends a message to the SQS queue. Amazon SQS redundantly stores the message across multiple Amazon SQS servers. Next, a consumer retrieves the message from the queue, and Amazon SQS starts the visibility timeout period. During the visibility timeout period, no other consumers can pick the message up from the queue. Then, the consumer processes the message and then deletes it from the queue during the visibility timeout period. Note that if the message is not processed and deleted from the queue before the visibility timeout period expires, another consumer might pick up and process the same message. You can perform these actions with the send message, receive message, and delete message API calls, either programmatically or from the Amazon SQS console. A variety of configuration options affect cost, message processing, and message retention. This slide illustrates how you might use the AWS command line interface, also called the AWS CLI, to call the send message operation. The send message operation delivers a message to a specific queue. The message body, which is the message to send, is a required parameter, and its maximum string size is 256 kilobytes. The queue URL is the URL of the SQS queue where a message is sent, and this parameter is required. Optionally, you might also include message attribute and delay seconds. After you send a message, the Amazon SQS response includes a Message Digest Algorithm 5, or MD5, digest of the message body string, which you can use to verify that Amazon SQS received the message correctly. The response also includes a system-assigned message ID, which is useful to identify messages. Additional elements might be included in the response depending on the message parameters and the type of queue. By using the receive message operation, you can retrieve one or more messages, up to 10, from the queue. You set the number of messages you want to retrieve by using the max number of messages parameter. Amazon SQS responds with a message or messages depending on the max number of messages that you set in the receive message command, as well as the number of records currently in the queue. For each record in the messages response, Amazon SQS returns a receipt handle for that message. This handle is associated with the action of receiving the message, not with the message itself. If you receive a message more than once, you get a different receipt handle each time you receive it. You need the receipt handle to delete the message or change its visibility in the queue. Immediately after a message is received using the receive message operation, Amazon SQS sets a visibility timeout. The visibility timeout is a period during which other consumers cannot receive and process the message. Before the visibility timeout expires, the consumer is expected to process and then delete the message from the queue. Amazon SQS doesn't automatically delete the message because, as a distributed system, there's no guarantee the consumer actually received and handled the message. For the duration of the visibility timeout, Amazon SQS temporarily stops returning the message as part of any receive message requests. This visibility timeout defaults to 30 seconds. The minimum is 0 seconds, and the maximum is 12 hours. You can use the visibility timeout parameter on the receive message operation to modify the visibility timeout for a receive message request. That's it for this video. Thanks for watching, and see you in the next video. For Part 2, Working with Amazon SQS Messages. For messages that cannot be processed and then deleted by the consumer, configure a dead letter queue in Amazon SQS. Dead letter queues can help you troubleshoot incorrect transmission operations and stop your queue from continually trying to process a corrupted message. The dead letter queue can receive messages from the source queue after the maximum number of processing attempts, max receive count, has been reached. The max receive count is set as part of the source queue's redrive policy. Messages can be sent to and received from a dead letter queue just like any other SQS queue. You can create a dead letter queue from the Amazon SQS API or console. To configure the dead letter queue from the console, first create a queue to be used as your dead letter queue. Then, on the source queue, choose to configure a redrive policy. As part of the redrive policy, select the queue to use as the dead letter queue and set the maximum receives option to tell Amazon SQS how many processing attempts to make before sending the message to the dead letter queue. In this example, the source queue is set with a redrive policy with a max receive count equal to 2. Because of the policy, message A is moved to the dead letter queue after the second consumer fails to process the message. Rather than making the message visible to consumers for a third time, Amazon SQS moves message A to the dead letter queue, and the message is no longer available in the source queue. Remember, consumers use a polling model to retrieve messages from an SQS queue. By default, when you make a receive message API call, Amazon SQS performs short polling, in which it samples a subset of SQS servers. Amazon SQS immediately returns only the messages that are on the sampled servers. In this example, short polling returns messages A, B, C, and D, but doesn't return message E. Short polling occurs when the wait time seconds parameter of a receive message call is set to 0. If the number of messages in the queue is small, fewer than 1,000, you will most likely get fewer messages than you requested per receive message call. If the number of messages in the queue is extremely small, you might not receive any messages from a particular receive message call. If you keep requesting receive message, Amazon SQS will sample all of the servers, and you will eventually receive all of your messages. By contrast, with long polling, Amazon SQS queries all of the servers and waits until a message is available in the queue before it sends a response. Long polling helps reduce the cost of using Amazon SQS by eliminating the number of empty responses when no messages are available for a receive message request, and false empty responses when messages are available but aren't included in a response. To enable long polling, set the wait time seconds parameter of the receive message request to a non-zero value between 1 and 20 seconds. Here's an example of a query to retrieve messages by using the receive message API from a queue named test queue. The query includes a few parameters to modify the default behaviors. First, wait time seconds is set to 10, which indicates that long polling is enabled. Next, max number of messages is set to 5, which indicates the maximum number of messages to return in a single call. In addition, visibility timeout is set to 15, which indicates that the message will be invisible to other consumers to process for 15 seconds. To prevent a message from being received and processed again when the visibility timeout expires, the consumer must delete the message. You can use the delete message operation to delete a specific message from a specific queue, or you can use delete message batch to delete up to 10 messages. To select the message to delete, use the receipt handle of the message. To use the delete message batch operation, provide the list of receipt handles to be deleted. The receipt handle is associated with a specific instance of receiving a message. If you receive a message more than once, the receipt handle is different each time you receive a message. When you use the delete message action, you must provide the most recently received receipt handle for the message. Amazon SQS automatically deletes messages that have been in a queue longer than the queue's configured message retention period. Take a few minutes to review the SQS message lifecycle again. Remember, You can perform these actions with the send message, receive message, and delete message API calls, either programmatically or from the Amazon SQS console. A variety of configuration options affect cost, message processing, and message retention. Here are the key takeaways for this section of the module. Developers use the send message, receive message, and delete message API operations to add, retrieve, and delete queued messages. Amazon SQS makes a retrieved message invisible on the queue for the duration of the visibility timeout. Amazon SQS can send failed records to a dead letter queue for separate processing. And short polling samples Amazon SQS servers for messages, while long polling queries all servers. That's it for this video. Thanks for watching, and see you in the next video. Covers Section 6, Introducing Amazon SNS. The Amazon Simple Notification Service, also known as Amazon SNS, is a fully managed messaging service with pub/sub functionality for many-to-many messaging between distributed systems, microservices, and event-driven applications. The service offloads message filtering logic from your subscriber systems and message routing logic from your publisher systems. Amazon SNS also reliably delivers messages and provides failure management features, including retries and dead letter queues. The service scales dynamically and offers a FIFO topics option, which works with FIFO SQS queues to preserve message order. An SNS topic is a logical access point which acts as a communication channel. Instead of including a specific destination address in each message, a publisher sends a message to the topic. Amazon SNS matches the topic to a list of subscribers for that topic. The service then delivers the message to each subscriber. Each topic has a unique name, which identifies the Amazon SNS endpoint for publishers to post messages and subscribers to register for notifications. A publisher can send messages to topics they created or to topics they have permissions to publish to. When you create an SNS topic, you can control access to it by defining policies that determine which publishers and subscribers can communicate with the topic. To receive messages published to a topic, you must subscribe an endpoint to the topic. After an endpoint is subscribed to a topic, the endpoint begins to receive messages published to the associated topic. Subscribers receive all messages published to the topics they subscribe to, and all subscribers to a topic receive the same messages. Amazon SNS supports application-to-application, or A2A, messaging with Lambda functions, SQS queues, Amazon Kinesis data firehose delivery streams, and HTTP or HTTPS. Amazon SNS supports application-to-person, or A2P, messaging using email, text, or SMS messaging, and mobile push notifications. When a message must be processed by more than one consumer, you can combine pub/sub messaging with a message queue in a fan-out design pattern. A fan-out pattern uses an SNS topic to receive a message, which is then pushed out to multiple subscribers for parallel processing. In the example on the slide, SQS queues subscribe to the new order topic. When a message is pushed from that topic, each queue gets an identical message but performs its own asynchronous processing. In this example, one queue hands off messages to an order fulfillment application, and the other queue interacts with a data warehousing application. Subscribers in a fan-out pattern can be a combination of endpoint types, including HTTP endpoints or email addresses. You could also use fan-out to replicate data that's sent to your production environment to your development environment. For example, you could subscribe yet another queue to the same topic for new incoming orders. Then, by attaching this new queue to your development environment, you could continue to improve and test your application by using data received from your production environment. In this example, the dev queue is connected to a Lambda function that anonymizes data before writing it to a development Amazon DynamoDB database. Here's an example of how you can use fan-out for image processing. When a user uploads images to an S3 bucket for image processing, a message about the event is published to an SNS topic. Multiple SQS queues are subscribed to that topic. When the SQS queues receive the message, they each invoke a Lambda function with the payload of the published message. The Lambda functions process the images. For example, generate a thumbnail image, size images for mobile applications or web applications, and send the results to another S3 bucket. That's it for this video. Thanks for watching, and see you in the next video. Covers Section 7, Developing with Amazon SNS. When a publisher sends a message to a topic, Amazon SNS returns a message ID and then attempts to deliver the message to all subscriber endpoints. Amazon SNS defines a delivery policy for each delivery protocol. The delivery policy defines how SNS retries the delivery of messages when server-side errors occur. That is, when the system that hosts the subscribed endpoint becomes unavailable. When the delivery policy is exhausted, Amazon SNS stops retrying the delivery and discards the message, unless a dead letter queue is attached to the subscription. Let's look at a few common API calls for Amazon SNS. The first is create topic, which creates a topic where notifications can be published. If a requester already owns a topic with the specified name, that topic's Amazon resource name, also known as ARN, is returned without creating a new topic. Second is subscribe, which prepares to subscribe to an endpoint by sending a confirmation message to the endpoint. If the service was able to create a subscription immediately without requiring endpoint owner confirmation, the response of the subscribe request includes the ARN of the subscription. To actually create a subscription, the endpoint owner must call the confirm subscription action with the token from the confirmation message. The next operation is confirm subscription. This verifies an endpoint owner's intent to receive messages by validating the token that an earlier subscribe action sent to the endpoint. If the token is valid, the action creates a new subscription and returns its ARN. Another operation is publish. This sends a message to all of a topic's subscribed endpoints. When a message ID is returned, the message has been saved, and Amazon SNS will attempt to deliver it to the topic's subscribers. The final operation we'll cover is delete topic, which deletes a topic and all of its subscriptions. Deleting a topic might prevent some messages that were previously sent to the topic from being delivered to subscribers. By default, an SNS topic subscriber receives every message published to the topic. To receive a subset of the messages, a subscriber must assign a filter policy to the topic subscription. A filter policy is a simple JSON object that contains attributes to define which messages the subscriber receives. When you publish a message to a topic, Amazon SNS compares the message attributes to the attributes in the filter policy for each of the topic subscriptions. If any of the attributes match, Amazon SNS sends the message to the subscriber. Otherwise, Amazon SNS skips the subscriber without sending the message. If a subscription doesn't have a filter policy, the subscription receives every message published to its topic. In this example, an online buyer visits a website, cancels one order, and places another order. These messages are published to the SNS topic shopping events. The payment SQS queue subscriber has a filter policy applied, so it receives only the messages about the orders. The Lambda function subscriber has a filter policy to receive only messages that the product page was visited. This slide highlights an example of a topic with a filter policy and example attributes that might be used to filter messages. When you publish a message to a topic, Amazon SNS compares the message attributes to the attributes in the filter policy for each of the topic's subscriptions. If any of the attributes match, Amazon SNS sends the message to the subscriber. In the online shopping example, the message attribute event type with the value product page visited matches only the filter policy that's associated with the search engine subscription. Therefore, only the Lambda function subscribed to the SNS topic is notified about the navigation event, and the payment SQSQ is not notified. Secure your Amazon SNS resources in 3 ways. First, consider identity and access management. Amazon SNS is integrated with IAM, so you can specify which Amazon SNS actions a user in your AWS account can perform with your SNS resources. You can specify a particular topic in the policy. For example, when you create an IAM policy, you can use variables that give certain users permission to use the publish action with specific topics in your AWS account. You can use an IAM policy to restrict user access to Amazon SNS actions and topics. An IAM policy can restrict access only to users within your AWS account, not to other AWS accounts. You can use an Amazon SNS policy with a particular topic to restrict who can work with that topic. For example, who can publish messages to it and who can subscribe to it. Amazon SNS policies can give access to other AWS accounts or users within your own AWS account. Next, use data encryption. Encrypt your data using server-side encryption, also known as SSE. SSE protects the contents of messages in SNS topics by using keys that are managed in AWS KMS. Third, protect internetwork traffic privacy. If you use Amazon VPC to host your AWS resources, you can establish a private connection between your VPC and Amazon SNS. With this connection, you can publish messages to your SNS topics without sending them through the public internet. Here are the key takeaways for the 2 Amazon SNS sections of the module. Developers publish messages to SNS topics, and subscribers to that topic get copies of all published messages. With attribute filtering, subscribers receive only relevant messages. Subscriber endpoints include both application to application, or A2A, and application to person, or A2P types. And Amazon SNS security includes managing access to SNS resources, protecting data sent to topics, and limiting exposure of messages to the internet. That's it for this video. Thanks for watching, and see you in the next video. It's now time to review the module and wrap up with a discussion of a practice certification exam question. In this module, you learned how to illustrate the way messaging services, including queues, pub/sub messaging, and streams, support asynchronous processing, describe Amazon SQS, and send messages to an SQS queue. You also learned how to describe Amazon SNS, subscribe an SQS queue to an SNS topic, and describe how Kinesis can be used for real-time analytics. Now, let's take a look at a sample exam question. A developer wants to introduce an asynchronous connection in their application workflow that processes individual banking transactions, including deposits and withdrawals. Transactions must be handled in the order they arrive. Which method would meet the developer's needs? A. Send transaction messages to a standard SQS queue. B. Put transaction messages onto a Kinesis data stream. C. Send transaction messages to a FIFO SQS queue. D. Put transactions onto a Kinesis data firehose delivery stream. Note the key requirements stated in the problem. The solution must process individual banking transactions, and they must be processed in order. Consider the answer choices and rule them out based on these key requirements. We'll pause a few seconds before discussing the correct answer. If you need more time to consider the answer choices, you can pause the video. So how do these answer choices compare to the requirements? First, a standard SQS queue cannot guarantee processing order, so that doesn't meet the requirement. For the second answer, a data stream is used to aggregate and analyze high-volume data rather than act on individual messages. The requirement requires processing individual records, which implies using a queue instead of a stream. Next, a FIFO SQS queue preserves message order, which meets the requirements. This could be the answer. Finally, using a Kinesis data firehose delivery stream. Again, the requirement is to process individual records, so a stream is not the best solution. The correct answer is C. The description of individual transaction processing implies that you need a queue. To ensure in-order processing, you need a FIFO queue instead of a standard queue. That concludes this module. Thanks for watching. We'll see you again in the next video.
Welcome to Module 11, Defining Workflows to Orchestrate Functions. We'll begin with Section 1, Introduction. By the end of this module, you should be able to recognize the dynamics of workflow coordination in distributed applications, describe AWS step functions, identify state types, indicate common use cases for step functions, and recall step functions API operations. In this module, you will learn about coordinating tasks in distributed applications and be introduced to step functions. You will then dive deeper into the step function service and learn about state types and use cases. Finally, you will learn more about the step functions API. Now that the coffee inventory is automatically updated on the cafe website, Frank would like to be able to request reports with the latest inventory information. Sophia thinks she can use step functions to coordinate the steps to generate a report. The inventory information is stored in an Amazon Relational Database Service database, or Amazon RDS database, and Sophia can create an AWS Lambda function to format the data into a report. She would like to use the Amazon Simple Notification Service, or Amazon SNS, to send Frank an email when the report is ready. Step functions can orchestrate those tasks into a workflow. The diagram on this slide gives an overview of the application that you will build through the labs in this course. The highlighted portions are relevant to this module. As highlighted in the diagram, you will create a step functions workflow and integrate it with a REST API. The workflow will coordinate the task of getting data from the database, generating a report, posting it to the Amazon Simple Storage Service, known as Amazon S3, and sending a notification through Amazon SNS. That's it for this video. Thanks for watching. I'll see you in the next video. This video covers Section 2, Coordinating Tasks in Distributed Applications. In modern cloud architecture, applications are decoupled into smaller, independent components called microservices. The compact nature of these components makes them easier to develop, deploy, and maintain in a cloud environment. In this example, we can see a traditional monolithic application on the left. On the right, the components have been broken up into microservices, which have been translated into Lambda functions. This is a high-level example of building applications from individual components. Each function can perform a discrete function or task. You can use a microservices architecture to deploy, scale, and update these application components quickly and efficiently. As an application grows in size, so does the number of components. And with the increasing size comes increasing complexity. You might have different patterns to run tasks. For example, this slide illustrates a serverless application built using Lambda functions. In it, a Lambda function is invoked immediately after another function, with the output leading to invocation of a parallel function, with that output fed into a choice function. As an application grows in size, the complexity of the functions we see here grows as well. You need a way to coordinate these components. By adding a coordination layer, you can provide the capability to automatically scale applications in response to changing workloads, handle errors and timeouts, and maintain application states. These features will help you build and operate your applications and can provide visibility and oversight to aid you in troubleshooting and tracking performance. Let's take a look at some of the key takeaways from this section of the module. Microservices are smaller, independent components that make up an application in modern cloud architecture. You can use microservices to quickly deploy, scale, and update application components. A coordination layer is necessary to handle automatic scaling, errors, and timeouts. Thanks for watching, and see you in the next video.